The atmosphere is far more than just the oxygen we breathe. It is a massive, pressurized shield held tightly to our planet by the constant force of gravity. At sea level, the atmosphere exerts a constant pressure of 101.3 kilopascals. This invisible weight acts as a structural force against our bodies and everything on Earth's surface. The atmosphere acts as a prism. Sunlight strikes gas molecules, scattering blue light in every direction. This is Rayleigh scattering. In an instant, if the atmosphere vanishes, sound disappears. Without molecules to collide, vibration cannot propagate. The world falls into absolute silence. The sky's blue hue is not an inherent color, but a result of scattering. As the atmosphere vanishes, that process halts, and the sky instantly turns the pitch black of the cosmos. In a vacuum, popular myths suggest the human body would explode. In reality, the process is much more subtle and deadly. The primary threat is embolism. Because atmospheric pressure vanishes, the boiling point of your body fluids drops below 37 degrees Celsius. Moisture in your eyes, lungs, and skin vaporizes instantly. Furthermore, trapped air in your lungs expands rapidly, posing a severe risk of lung rupture. In an atmosphere-less environment, the fundamental problem for objects is the pressure differential between their interior and the vacuum of space. Think of our structures like a pressurized vessel. Deteriorating seals, cracks, or gaps become failure points when the external support disappears. Consider high-altitude aircraft. They are designed to maintain internal pressure. If the external atmosphere vanishes, the load on the fuselage exceeds design limits instantly. Sealed windows and pressurized containers shatter. The building itself may stand, but glass and non-reinforced structures succumb to the rapid outward force. The most dangerous part is not the vacuum, but the return. After 10 seconds, the atmosphere rushes back. This return creates a global supersonic shockwave. Air molecules slam back into Earth at speeds exceeding Mach 1, resulting in a worldwide catastrophic explosion. When the atmosphere rushes back after 10 seconds, it is not a gentle return. It is a catastrophic global shockwave. This process triggers adiabatic heating. As air compresses rapidly, its kinetic energy spikes, resulting in extreme localized heat. The re-entry is essentially a global blast wave. The collision of molecules at supersonic speeds creates a shock front similar to a massive explosion. This combination of supersonic shock waves and extreme adiabatic heat would prove fatal to any remaining biological structures. Even a fleeting 10-second atmospheric gap would trigger a massive disruption in the ionosphere. This region, extending hundreds of kilometers, relies on a steady balance of ionized particles. With the ionosphere compromised, all satellite-based navigation and global communications would vanish instantly. GPS systems, crucial for modern infrastructure, would lose their signal link to the ground. Normally, the ionosphere filters solar radiation. Without its protection, electronics are exposed to unchecked solar flares, compounding the hardware failures. The recovery process is not immediate, because the entire layer of ionized particles must be regenerated by solar radiation. Stabilization could take weeks of chaotic signal noise and geomagnetic instability. While the loss of Earth's atmosphere is physically impossible, this scenario acts as a powerful theoretical model for planetary science. Researchers use these extremes to map the boundaries of exoplanet habitability. By simulating sudden atmospheric loss, we better understand how planets retain life-sustaining gases. It also reveals the dynamics of thin atmospheres. Observing how a planet reacts to rapid decompression helps us predict the stability of worlds with lower gravity. Furthermore, this exercise refines safety protocols for space habitats. Understanding structural stress under extreme pressure gradients is vital for future colonization. Ultimately, this is a lesson in planetary physics. It reminds us that our atmosphere is not just a shield, but a delicate, pressurized system essential for every aspect of life on Earth.